Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY 212, we are at the lecture number 20 and the topic is Hermitian operators. As we know that quantum mechanics is a operator mechanics, which means that for every observable we have a corresponding operator which acts on a function, that is a wave function, and gives us an eigenvalue. Now that eigenvalue is measurable quantity because it's a real quantity, and we can then correspond our quantum mechanical theory to the real world. So it means that we must have in our quantum mechanics operators that produce eigenvalues which are real. Now the question is whether all operators produce real values, and the answer is no. Only few operators or some class of operators produce eigenvalues which are real, and these are called Hermitian operators. In today's lecture, we will understand that how Hermitian operators are defined and how the eigenvalues of Hermitian operators are real. So let's start with the expectation value of an observable. You know that the average of an observable A in the state psi is given by this formula, where on the left side you see this is the expectation value of any observable. This observable could be the position of the particle, or could be the energy of the particle, or could be the momentum of the particle, and it is defined in the integral psi star psi, and between them is the operator corresponding to that that observable. Now this wave function, that is psi star, and psi star is the conjugate of the psi, is the function, wave function, on which this operator is acting, and when this operator acting on psi will give us some eigenvalues, and these eigenvalues we demand to be real. So what are the choices for us for this wave function, or what are the possible types of wave function we can have for this corresponding operator? And by the way, this next equality is only the change of notation from the standard notation to the bracket notation. So here you can see this psi is corresponding equal to psi star, this bra, and ket is corresponding to the psi. So the question is now that what are the possible state functions we can have over here, and I will give you a few examples of it just to give you an understanding that this psi is not unique, and we can have possible wave functions on which this A can act and will produce to us eigenvalues. So the possible states are the following. For example, psi 1, this is one of the possible states for the any observable, and here you can see B e raised to power minus x square a square, where B is a normalization constant. And then we can have another possibility, psi 2, it is C e raised to power iota kx by x, and C is a normalization constant, and this is yet another possibility. And you can construct so many other possibilities for these wave functions. But remember that this B, C are the possible wave functions we can have, possible normalization constants in the wave functions which we can have. Okay. So the expectation value of an observable must be real. This is our demand, and it must be real for any state function that I shown you the all possible wave functions. These are the all possible wave functions, but the expectation value of any observable must come out of any of these possibilities must be real. So the demand is that here this expectation value must be real. Okay, it cannot be complex, or it cannot be imaginary. And why? Because real world is giving us real values, not complex or imaginary values. So if you perform any experiment in the real world, you will find out some real value. So any theory which is describing our real world shall also produce give us some real numbers to test. So this is constraint coming from the physical world. Okay, One of the examples for the observable which we can measure is the energy, and the corresponding operator to the energy is Hamiltonian, this H hat. So what we are saying that this E, which is the observable and expectation value of observable, it is not the exact value, mind you, this is the expectation value, which means this is the average value. So if we prepare large number of replicas of some system and measure energy in each of them, then the answer will not come same all the time. It will be a different answer. So what we can do that at the end we can take average of all these answers, which is called expectation value, and it is defined like this. And if you put the value, the equation or the representation of H bar in terms of differential operators, so this is its form, and if you calculate it, what we are demanding that this E energy must be real. So that's very physical and that's very logical assumption, demand or constraint, that the expectation value of energy corresponding to this H hat acting on this wave function must be real. But the problem is that all sorts of operators will not produce these real values, and our today's topic is about to find out those operators which are producing real values, and we call them Hermitian operators, or to construct operators in a way that they are Hermitian. So Hermitian operators are the class of the operators that have real eigenvalues, which means that they are producing us something which we can test in our experiments. And in quantum mechanics, the operators corresponding to observables are required to be Hermitian. So this is a very strict, or you can say a very logical requirement or constraint from quantum mechanics, that any operator one uses in quantum mechanic equations must be Hermitian. Actually, mathematically one can use any kind of operator, and it is not needed that the operator is real valued, produces real eigenvalues or Hermitian, since quantum mechanics is a theory of nature, it's a physical theory. Therefore, we demand that this theory can have only operators which are Hermitian or produce eigenvalues which are real. So how to calculate then, how to confirm that some operator is a Hermitian operator? For this purpose, we will first calculate the Hermitian adjoint of an operator. And how can we calculate the Hermitian adjoint? The Hermitian adjoint is calculated as in the following. Consider the operators, this A and another operator, A dagger. So these are the two operators, and we want to know that whether these two operators are Hermitian are Hermitian or not, or this operator A is Hermitian or not. So the simple answer is to compare A with the A dagger. If A is equal to A dagger, we say that it is Hermitian, otherwise it is not. And this A dagger is called the Hermitian adjoint of this A. So this is the Hermitian adjoint. So what is the definition of the Hermitian adjoint of an operator is then that suppose we have two operators, the same operators A and A dagger, and at the moment you can consider that they are not related, they are completely different. But if A is a real one, and it will act on the bra, that is the real wave function, then there will be a dagger, and a dagger is calculated by taking the complex conjugate of A and also taking the transpose. So therefore it is sort of complex conjugate of A. So this A dagger by definition we will say will not act on psi, but will act on, or will not act on bra. It will not act on bra, but it will act, it will not act on cat, but it will act on bra over here, where this A will act over here, as you can see. So in this here, you see that A dagger is actually acting on the bra, and A is acting on this. At the end, this requirement we will develop at the end, but at the moment you can just see that the adjoint of an operator is acting on the bra, and the operator itself is acting on the wave function, real wave function. So or the cat, it is acting on the cat. So at the end we will also require that this A and A dagger are equal, that's why they are called Hermitian. But at the moment, just to define adjoint operator, you think of it like it is acting on the bra. So whenever there is an adjoint operator, it will act on bra and not in cat. Okay. Examples of it, of Hermitian adjoint. The first of all, if you have any complex number, so what will be, it's just a number, it is not a matrix. For example, if you have 2 iota, this is a complex number, let's say this is C. This is so what will be the Hermitian adjoint of this complex number? And it is clear that dagger is only to take the conjugate, that is minus 2 iota will be a C dagger in this case. So if we have a complex number and the complex numbers taking complex conjugate of that number, or taking the conjugate will give us the C dagger. So this is a simple example of a Hermitian adjoint of any operator. In future, in future slides, I show you that how to calculate the Hermitian adjoint of some complicated operators. Okay, so again, if operator is some real number, and if for example this operator is a real number or some complex number, so there is another way to know that what is the Hermitian conjugate of it. So what we know that A dagger will act on the cat, on the bra, and then A can will act on the cat, and these two are same because it's this A is an operator and A dagger is the Hermitian adjoint of it. And you know that in bracket notation we learned that we can take out A outside the bracket notation, and if we take out or out it here, and then we can, if put it back, we can put it back to with a bra, but then we will have to take the complex conjugate of it. So from here we know that the A dagger of A is A star. So what I want to tell you that this is the proper way of calculating the Hermitian adjoint of any operator. So for example, if you know that this is an operator A and you want to know its Hermitian adjoint, what you can do is that calculate these steps. That is, first start A dagger with the bra, and then you can know how to bring it into the cat, and then from here we know now this A dagger is equal to A. So this way is the proper calculation for Hermitian adjoint. Okay, as I told you that I will give you more interesting examples or more complicated examples of calculating Hermitian adjoint. So consider that another operator which is a partial derivative with respect to x, that is del by del x, and now we want to calculate its Hermitian adjoint. Then it's simple that this d, since it's a real one, is acting on psi, but we can transform it into this integral notation. And here you see it is acting on psi, but then we can integrate this thing by partial integration and shift this derivative on first function. So this is the surface terms, and then we know that this del by del x is on psi star, and then the surface terms vanish because on the boundary there is no wave function, and there you get minus sign, and now you know what is d dagger. Okay, so this is the proper way. In the last example, we actually this calculated easily because without integral, because it was a very simple operator, just multiplicative operator. A was multiplying with the wave function. But now since we have an operator over here which is not simple a multiplication but taking a derivative, so we needed this integral, and we calculated this integral and knew that what d dagger is. So this is an example how you can calculate the adjoint of an operator. Okay. So why we wanted to calculate an adjoint of an operator? Because we wanted to know that whether operator is a Hermitian or not. And this is the condition that a Hermitian operator is an operator which is equal to its Hermitian adjoint. So if I want to know that if some operator is Hermitian, or in other words, it will produce to me eigenvalues which are real, then what I will do, I will first calculate its a Hermitian adjoint, as I did in 2 examples before. And if it came out to be equal, I say that this is actually a Hermitian operator. For example, in this case, you know that this is not an Hermitian operator because d dagger is not equal to d, it is equal to minus d. But In future we will see, and this is a condition in terms of bracket notation, that it is acting on psi and it is written psi. If this is equal, I say this is a Hermitian operator. So now let me give you the examples of Hermitian operators. We will start with the simple one, and then we'll construct the interesting ones and even ones which are physically interesting to know. That is the energy momentum operator. Okay, so let's start for a real number. So if I have a real number, actually we have did this example already. This A is an operator which is acting with a psi, and this A will come out to be A star. So this is that requirement they are fulfilling, and we know that real number, since it's real, A star is equal to A, that is A star is actually equal to A because it's real. So it means that this real number is actually a Hermitian operator. And what are the properties? Now we want to check what are the properties of some Hermitian operators. And remember that at the end I will give you calculation for energy momentum operators to check whether they are Hermitian or not. So after giving these examples for properties, I will also give you tell you how to calculate the Hermitian operators for energy and momentum. Okay, so first of all, if you have two operators multiplied and then you take the Hermitian adjoint of it, then it is equal to B dagger A dagger, because if they are even matrices, then you have to change the order to make them multiplicable. So if A and B are Hermitian, then we want to know that if AB dagger is equal to BA, then if this AB plus BA, this bilinear, we call it a bilinear, if this bilinear operator is Hermitian or not. So the purpose of this calculation is to check whether this bilinear combination is actually Hermitian or not, and this we can simply check by taking this dagger to all the quantities and then using this quantity over here, and we see that this is B hat, A hat, A hat, B hat, and then since it is commutative, you can take it here or here, and then since they are equal, so we know that this bilinear is actually Hermitian operator. Okay, then another one is to check whether the square of an operator is Hermitian or not. So let's do a calculation. So A hat square is equal to A dagger. So A hat square can be written as A hat, and then this dagger can be taken to both of them, first one and the second one. And since an operator is already defined as a Hermitian, so A dagger will be equal to A and A. So again A hat is equal to A hat square. So by this we know that the square of a Hermitian operator is also Hermitian. There is another way to calculate, as this was doing from arithmetics, but if you want to properly check if the square of the Hermitian operator is Hermitian, then you know that A dagger we will put over here for square, then this we will first take it to the bra, and this will come here, and this another we can take it again or bra. You will be wondering why I am not writing dagger over here, because we know that it is Hermitian, because we already know that A dagger is equal to A. So there is no need to again put dagger over here because it is Hermitian. We are saying that it is Hermitian, so we can just bring it over here without dagger, because a dagger is equal to A, and this both coming over here. So now we know that they both acting on the bra, and from this we know that the square of the Hermitian operator is actually Hermitian. And as I promised, then to calculate the momentum energy operators to check whether they are Hermitian, and they must be Hermitian, because momentum and energy are two observables which we measure every day, and for all quantum mechanical systems we measure momentum and energy, and if they are not producing the real values, then there is something very wrong with our theory, fundamentally wrong. And so it's a good check to know, to check these things, that whether momentum and energy operators are Hermitian or not. So let's start with the momentum operator. You know that P hat, and what will be the condition? That this P hat acting on psi n must be equal to P hat acting on psi l, because by the Hermitian operator we know that P hat dagger must be equal to P hat. So therefore I have written over P hat, not P hat dagger. So let's do the calculation, and these are the calculations. We know that P hat is equal to del by del x, and then this is as we already done for the case of simple D operator, del by del x, and it comes out to be the same one. Here you must note that in the definition of p hat, and it's very interesting point, and helps you to understand that why p hat is constructed in this way. So now you know that the p hat is constructed in way minus I h bar del by del x. And why we put this minus iota here? So many people ask me that why there is minus I sign, imaginary sign. And there is a reason coming for you. In previous example, if you remember this, let's go back to that example here. Here you see that in this del by del x, when there was no minus iota, minus I sign, it came out to be with a minus sign and it was not Hermitian. And since we require in quantum mechanics our operators to be Hermitian, now we have to make this operator Hermitian. And the only way we could convert it into Hermitian operator was to put this minus I over here. And what this minus I is doing, when you do the integration by parts, so this surface term anyway goes away, and here you see, because there is a minus sign, and because of the minus we got a minus, another minus, and it is now plus. Okay, and because of the iota we could take it over here, in the complex thing, and when in the complex thing, when I take this minus I inside into the star, now when I take star I have to change its sign, it will become from minus to plus, and then this thing is actually the p, because if you take the star of it, conjugate of it, and its minus is plus, it giving you exactly the p, and here we know that this is the p. So and this h bar is actually just the quantum mechanical, to make it quantum mechanical, this operator h bar, or it comes actually from dimensional analysis. This is another interesting point, a good point, that this h bar is coming from a dimensional analysis, because this p has to be linear momentum, and this h bar is an angular momentum, but linear momentum with del by del x. So here you can check that this h bar is angular momentum and this x is position. So angular momentum divided by position will give you something linear momentum. So this h bar is coming in the definition from the dimensional analysis, dimensional requirement to be equal, and this I coming in the definition because to make it Hermitian. So that's why we define operator in this way. So now from this explanation, you can infer how to define operators. The most important requirement is that they must be Hermitian. Okay, next we go for a free particle. In free particle case, our H will be okay. We go for the energy operators. Okay, now we want to calculate the know whether the energy operator is Hermitian or not. We know that the corresponding operator for energy observable is Hamiltonian, and Hamiltonian for free particle is p square by 2m. It's very simple to check whether it is Hermitian or not, because we know already that the square of an operator is Hermitian. So that's done. This 2m is constant. So p square must be Hermitian. If p is Hermitian, then p square must be Hermitian. And we have already checked for p in a momentum case that it is Hermitian. So p square is also Hermitian. But you can check, take a dagger of it and come. And this was for the free particle. That is the particle on which there are no forces acting upon. So therefore, it was a free particle. But in case you have a potential for it, then you can also check that if there are forces acting on some particle, that is there are some kind of potential existing, then whether this H is Hermitian or not, then we can check it as well. We have to check only this term, because this term is already done. So this term is very easy, because it's it's only a multiplicative one. So you can put it over here, and you can just bring it over, because it's just a number. It's a just real number. We have already now. This is another interesting point, that at the beginning, when I was giving you the real numbers Hermitian thing, you would be wondering that it's very trivial why you are telling us. But now here you can see that if the potential is real, you can just take it to the bra side, and you can know that it is Hermitian. So by this we know that our energy operator is also Hermitian in case of free particle and in case of particle which is under some potential. So, what we have done in our today's lecture, that we have checked in detail that the Hermitian operators, and what are Hermitian operators? These are the operators which we really need to connect our quantum mechanics with the real world or the experiments outcomes, because experiments outcomes are real or the daily life observation must be are actually real values. So therefore our quantum mechanics shall produce quantities which are measurable and real valued. And since quantum mechanics is not a simple mechanics, it's an operator mechanics, it has operators with it which are corresponding to some observable, and when they act on some functions they produce eigenvalues. So we have to make sure these eigenvalues are real valued. For this we make our operators Hermitian, that is the adjoint of any operator is Hermitian adjoint of any operator is equal to that operator, then its eigenvalues are guaranteed to be real. That's why all the operators in quantum mechanics corresponding to some observables are required to be Hermitian. With this, I say thank you to you.